Now we discuss chapter 9. The title of this chapter is Conformal Mapping and Bilinear Transformation. We divide this chapter into 4 modules. In module 1, we discuss about conformal mapping and some of its properties. In module 2, we discuss basic properties of bilinear transformations. In module 3, we discussed about fixed point of a bilinear transformation, and in module 4, we discuss about inverse point with respect to a circle. So, now we discuss module 1. The title of this module is Conformal Mapping. We recall that a curve z equal to zt equal to xt plus iyt is called regular curve if the derivative of xt and yt exist continuous and do not vanish simultaneously. A regular curve can be characteristic by having tangent at every point. Our purpose is to compare the inclination of the tangent at a point of a curve together with the inclination of the tangent of its image curve at the image point. Let w equal to fz be a complex valued function of a complex variable z. To each point z0, there is image point w0 equal to f of z0. This means that for finding image of a point or a curve, we need another complex plane to sketch the image. We called it as W plane. In this module, we discuss mapping which transforms different curves or region from one complex plane to another complex plane. We also discuss an important result known as Riemann mapping theorem. At last, we provide some example relating to this module. We now start our presentation. So, we start about conformal mapping. So, a mapping or transformation W equal to Fz which preserves angles in magnitude and sense between every pair of curves passing through a point is called conformal at that point. If a mapping is conformal at every point of a domain D, then it is called conformal in D. On the other hand, if the mapping W equal to Fz preserves angles in magnitude but not in sense, is called isogonal mapping. An example of such a function is Fz equal to z bar. The function Fz equal to z bar maps the positive real axis and positive imaginary axis onto the positive real axis and negative imaginary axis respectively. Although the two curves intersect at right angles in each plane, but a counterclockwise angle is mapped onto clockwise angle. Now we define critical point. Let Fz be a non-constant analytic function in a domain D. If first derivative of f at z0 equal to 0 for some z0 belongs to D, then the point z0 is called the critical point of that transformation. Clearly, z equal to 0 is the critical point of the transformation w equal to fz equal to 2z cube minus 1. It is also to be noted that a constant map has no critical points. Now we consider an example. Find the critical points of the mapping w equal to e to the power 2z minus 2iz plus 3. Since w equal to fz equal to e to the power 2z minus 2iz plus 3 is non-constant and analytic for all z in the complex plane, it follows that its critical points are the values of z for which f dash z0 equal to 0, and therefore twice e to z minus 2I equal to 0, that is e to the power 2z equal to I, and which is equal to e to the power I into 2n pi plus pi by 2, and this gives the value of z as z equal to I into n pi plus pi by 4, where n belongs to I, the set of all integers. So now we consider a result. Let fz be analytic in a domain D. If at each point z belongs to D, f dash z is not 0, then the mapping w equal to fz is conformal in D. So proof, let C1 and C2 be two continuous curves in the z plane intersecting at z0. Let the tangents of C1 and C2 at z0 make angles alpha 1 and alpha 2 respectively with real axis. Suppose that z1 and z2 are 2 points on C1 and C2 respectively at a distance r from z0, where r is small. Therefore, we have z1 minus z0 equal to r e to the power I theta 1 and z2 minus z0 equal to r e to the power I theta 2, where theta 1 tends to alpha 1 and theta 2 tends to alpha 2 whenever r tends to 0. Let gamma 1 and gamma 2 be the image curves of C1 and C2 in the W plane. Let W0, W1, W2 be the images in the W plane of the respective points Z0, Z1, Z2 in the Z plane. We also suppose that the tangents of gamma 1 and gamma 2 at W0 make angles beta 1 and beta 2 respectively with real axis. Then W1 minus W0 equal to rho 1 e to the power I phi 1 and W2 minus W0 equal to rho 2 e to the power I phi 2, where phi 1 tends to beta 1 as rho 1 tends to 0 and phi 2 tends to beta 2 as rho 2 tends to 0. So this is the figure. So here in the Z plane we take two continuous curves C1 and C2. The tangents at Z0 of C1 makes angle alpha 1 with real axis, and tangent at W0 of the curve C2 make angles alpha 2 with positive real axis, and we take W0, W1, W2 as the image point of Z0, Z1 and Z2 respectively, and gamma 1 and gamma 2 be the image curves of C1 and C2. Suppose the tangent of gamma 1 at W0 make angles beta 1 with real axis, and tangent of gamma 2 at W0 make angles beta 2 with real axis. Now f dash z0 is equal to limit z1 tends to z0 f z1 minus f z0 by z1 minus z0, and that is equal to limit z1 tends to z0 w1 minus w0 by z1 minus z0, and that is equal to limit z1 tends to z0 rho 1 by r e to the power I phi 1 minus theta 1. Since fz is analytic at z0 and f dash z0 not equal to 0, we can write f dash z0 equal to r e to the power I lambda, where r is given by modulus f dash z0 and lambda is given by argument f dash z0. So, from this we obtain r e to the power I lambda equal to limit z1 tends to z0 rho 1 by r e to the power I phi 1 minus theta 1, which gives lambda equal to limit z1 tends to z0 phi 1 minus theta 1, that is equal to beta 1 minus alpha 1, that is beta 1 equal to lambda plus alpha 1. So, similarly we can obtain beta 2 equal to lambda plus alpha 2. This gives beta 1 minus beta 2 equal to alpha 1 minus alpha 2. This shows that the angle between gamma 1 and gamma 2 at W0 is the same in magnitude and sense as the angle between C1 and C2 at Z0. Hence, the mapping W equal to Fz is conformal at Z0. Since Z0 is an arbitrary point in D, the mapping W equal to Fz is conformal at every point of D. This proves the result. So, note the function Fz equal to e to the power z is conformal everywhere in the complex plane, because e to the power z is an entire function and f dash z equal to e to the power z, which is not 0 for all z. The map W equal to z to the power n is conformal at all points except z equal to 0, which is a critical point. The function fz equal to sin z is analytic everywhere and hence represents a conformal mapping except at the critical points z equal to 2n plus 1 pi by 2, where the derivative f dash z vanishes. Again, the function fz equal to z square plus z plus 1 is conformal except z equal to minus half, because it is analytic everywhere and f dash minus half equal to 0. So, another note, to see how conformity may fail at a point z0 where f dash z0 equal to 0, we consider the function fz equal to z square, then f dash 0 equal to 0. Now, if gamma 1 is the positive real axis from 0 to infinity and gamma 2 is the imaginary axis in the upper half plane, then the image of gamma 1 under f, that is f of gamma 1 equal to capital gamma 1, is the positive real axis from 0 to infinity, and f of gamma 2 equal to capital gamma 2 is the negative real axis from 0 to minus infinity. We see that the angle between gamma 1 and gamma 2 is pi by 2, whereas the angle between their image curves capital gamma 1 and capital gamma 2 is pi. Thus, fz equal to z square is not conformal at 0, although it is conformal at every other point of the complex plane. Another note, if W equal to Fz is conformal at Z0 and a function hz equal to g of fz defined in some neighborhood of fz0 is conformal at this point, then the composite map GF is also conformal at the point z0. So, now we consider an example so that the mapping W equal to Fz equal to cos z is conformal at the points I 1 and pi plus I, and determine the angle of rotation given by alpha equal to argument f dash z at the given points. So, here f z is cos z, therefore, f dash z equal to minus sin z. The mapping W equal to f z equal to cos z is conformal at all points except z equal to n pi, where n is an integer. Therefore, f dash I equal to minus sin I, which is equal to minus I sin hyperbolic 1, f dash 1 equal to minus sin 1, and f dash pi plus I equal to minus sin pi plus I, which is equal to I sin hyperbolic 1. Thus, the angle of rotation is given by alpha 1 equal to argument f dash I equal to minus pi by 2, alpha 2 equal to argument f dash 1 equal to pi, and alpha 3 equal to argument f dash pi plus I, which is equal to pi by 2. So, now we consider another result. Let Fz be analytic at a point Z0 belongs to D. If f has a 0 at Z0 of order k minus 1, then the mapping W equal to Fz magnifies angles at Z0 by k times. So, proof: since Fz is analytic at Z0, it has a Taylor series expansion about Z0 of the form Fz equal to summation n equal to 0 to infinity a n z minus z0 to the power n, where a n is given by nth derivative of f at z0 by factorial n. Since f has a 0 at z0 of order k minus 1, we have f dash z0 equal to f double dash z0 equal to k minus 1th derivative of f at z0 is equal to 0. So, we obtain fz equal to f z0 plus a k z minus z0 to the power k plus a k plus 1 z minus z0 to the power k plus 1 plus etc., and which gives fz minus fz0 equal to z minus z0 to the power into hz, where hz is analytic at z0 and hz0 not equal to 0. Now, putting w equal to fz and w0 equal to fz0 in above equation, we obtain argument w minus w0 equal to k into argument z minus z0 plus argument hz. Assume that z tends to z0 along a curve gamma, then obviously w tends to w0 along the image curve capital gamma. The slope of tangent to the curve gamma at z0 and that of the tangent to the curve capital gamma at w0 are connected by the relation limit w tends to w0 argument w minus w0 equal to k into limit z tends to z0 argument z minus z0 plus limit z tends to z0 argument hz, that is theta 0 equal to k into phi 0 plus argument hz. Therefore, if gamma 1 and gamma 2 be two curves passing through z0, and their image curves capital gamma 1 and capital gamma 2 under the mapping W equal to Fz pass through W0, the difference of slopes of the curves gamma 1 and gamma 2 at Z0 and that of the curves capital gamma 1 and capital gamma 2 at W0 are related by theta 2 minus theta 1 equal to k into phi 2 minus phi 1 with the sense remain unchanged. This proves the result. Now we consider an example. Suppose Fz equal to sin z, then F is entire and F dash z is cos z, so that F dash zn equal to 0 for zn equal to 2n plus 1 pi by 2, where n is any integer. Thus, F is conformal in C except the points 2n plus 1 pi by 2. Note that F double dash z equal to minus sin z and F double dash zn not equal to 0 for each n belongs to the set of all integers. Therefore, by theorem 2, the angle between any two rectifiable curves intersecting at Zn is increased by a factor of 2 by the mapping W equal to Fz. So far we have discussed about conformal mapping, isogonal mapping and critical point. We also discussed that if F is analytic at a point Z0 and if F dash Z0 not equal to 0, then the mapping W equal to Fz is conformal at Z0. Now we will discuss an important result in complex analysis known as Riemann mapping theorem, which tells that there is nearly an analytic function which maps a given simply connected domain onto another given simply connected domain. This theorem has a far-reaching implication in the theory of function of a complex variable. At last, we provide some example. We now go to our presentation. We now discuss some general transformation. To discuss this, we assume that alpha and beta are given complex constants, while a and theta are real constants. So, first we define translation. The transformation of the form W equal to Z plus A is called translation. By this transformation, figures in the Z plane are translated in the direction of A. So, now rotation, the transformation of the form W equal to e to the power I theta into Z is called rotation. By this transformation, figures in the Z plane are rotated through an angle theta. If theta positive, then the rotation is counterclockwise, while if theta is negative, the rotation is clockwise. So, now stretching, this type of transformation is of the form W equal to Az. By this transformation, figures in the Z plane are either stretched or contracted in the direction Z if A greater than 1 or if 0 less than A less than 1. So, another is inversion. The mapping of the form W equal to 1 by Z is called inversion. So, now the Riemann mapping theorem, two simply connected domains D1 and D2 in complex plane are said to be conformally equivalent if there exists an analytic function phi from d1 to d2 such that phi is 1 1 and on 2. The Riemann mapping theorem in its common form asserts that any two simply connected proper subdomains of the complex plane are conformally equivalent. That is, if d1 and d2, which are not the whole complex plane C, are simply connected domains, there exists a 1 1 analytic map of d1 onto d2. Note that the condition that d1 and d2 not equal to whole complex plane C is necessary as a consequence of Liouville's theorem. So, now we state the theorem. Suppose D is a simply connected domain other than the whole complex plane and Z0 is a point in D. Then there exists a unique function fz analytic and 1 1 in D which maps D onto the disk mod w less than 1 in such a manner that f of z0 equal to 0 and f dash z0 is greater than 0. For proof of this theorem, please see any reference book. Now remark, there exists no conformal map that maps the entire complex plane onto unit disk. It must be emphasized that Riemann mapping theorem is applicable to only simply connected open sets and says nothing about the behavior of the mapping function on the boundary. Now we consider an example so that the mapping w equal to fz equal to z square maps the rectangle R equal to x plus iy such that minus 1 less or equal to x less or equal to 1, 0 less or equal to y less or equal to half of unit area onto the region enclosed by the parabolas v square equal to u plus 1 by 4 and v square equal to minus 4 into u minus 1. So, solution, since fz equal to z square, we have f dash z equal to 2z and the mapping w equal to z square is conformal for all z not equal to 0. The right angles at the vertices z1 equal to 1, z2 equal to 1 plus I by 2, z3 equal to minus 1 plus I by 2 and z4 equal to minus 1 are mapped into right angles at the vertices w1 equal to 1, w2 equal to 3 by 4 plus I, w3 equal to 3 by 4 minus I and w by 4 equal to 1 respectively. And for this, see this figure. So, this is the rectangle having vertices at 1, 1 plus I by 2, minus 1 plus I by 2 and minus 1, and their images are the points 1, 3 by 4 plus I, minus 1 by 4 and 3 by 4 minus I. The parabolas shown in the figure are obtained as follows. Let w equal to u plus iv, then u equal to x square minus y square and v equal to 2xy, because w equal to z square. The line x equal to 1 corresponds to the curve u equal to 1 minus y square and v equal to 2y. Eliminating y, we obtain v square equal to minus 4 into u minus 1, which is a parabola having vertex at 1 0 and open towards the negative side of the u axis in the w plane. Also, the part of the line x equal to 1 lying above the real axis corresponds to the part of the parabola lying above the u-axis in the w plane. The same parabola in the w plane is the image if the line x equal to -1. In this case, the part of the line x equal to -1 lying above the real axis corresponds to the part of the parabola lying below the u-axis in the w plane. When y equal to half, we obtain u equal to x square minus 1 by 4 and v equal to x. Eliminating x, we obtain v square equal to u plus 1 by 4, which is also a parabola with vertex minus 1 by 4 0 and open towards the positive side of the u axis in the w plane. By similar arguments as before, we can say that the mapping w equal to fz equal to z square maps the rectangle R of unit area onto the region enclosed by the parabola v square equal to u plus 1 by 4 and v square equal to minus 4 into u minus 1. At the end of this module, we came to know about conformal mapping, isogonal mapping and critical point. We also came to know about the relation between conformity and analyticity of a function. We also discuss Riemann mapping theorem. This is a powerful result and is used in wide range of mathematical settings. We also provide some examples related to this module. For more problems, please see the self-assessment part and also consult any reference book for further details. This ends module 1 of chapter 9.